Clark relativity, step 2, dilation of mass. Well, dilation of mass, just like a dilation of time and contraction of length, it's come from the relativistic effect. It's a lambda, this factor. Okay, so one thing I didn't emphasize enough in the step 1 is when Einstein proposed this relativistic theory, special relativity, he makes sure a few things. One, if V is in inertia frame, V is very small, then it's resolved to Newton, the classical physics, right? And also physics law is same and consistent within a frame. So everybody, including scientists, live in one frame, and whatever he observed there and make a physics law should be same as other scientists living in different frame. Okay, so this is the very important requirement for Einstein, right? So what's happened is there are many other implications of this equation, basic equation we learned in step 1. Okay, if you look at the momentum is m0, and the guy moving is going to be this. There's no negative here. Actually this is gonna be m. So since lambda is going to change, the mass must change. So for observer A, the B's mass going to be something like that. It's called infinity near speed of light, maximum speed. Okay, so this is something new, the new reality in the physics. The Newton never had it because Newton was working in this area. Okay, so this is called the dilation of mass, and we manipulate equation a little bit more, try to calculate energy. Energy will be 2-part. Okay, the energy has the m0 is the intrinsic mass at the rest, c to get c square. So every mass contains this much energy, plus kinetic energy, which is Pc, the mv. P is mv, momentum times c. So this is kinetic energy. So when particles moving at the speed of light, it's going to be m equals c, the E equal mc square, and that's contain both. m0 is intrinsic energy, it's every mass is energy. Okay, and plus kinetic energy. Okay, so what's happened is the kinetic energy increase as particle move faster, and energy become eventually infinity at the maximum speed. But at the rest, still has energy, which is the m0 c square. And this rest energy, is there any way to get it out? That's a nuclear energy, right? So m0 we split into m1, m2, then some m lost that convert to the energy. So m0 c square becomes m1 plus m2 plus delta m c square, and m1 c square is another rest energy for one atom plus m2 different atom plus delta m c square, and that's going to be the heat. That's a nuclear energy. Okay, so in the classical physics we had to reconcile with classical physics. Kinetic energy is 1 over 2 mv square. It doesn't look like the Einstein's special relativity gives this. Where this come from? Because we have a 1 over 2. Well, actually the kinetic energy has a lambda. If you expand the lambda into the series, then here you go, 1 or 2. And if v is much smaller than c, then you eliminate the higher term. So energy equals mc square equals m0 c square 1 plus b square c square. So it's going to be at the end total energy is the mass at the rest c square plus 102 m0 v square. That's what we've been dealing with in the Newton's mechanics. Okay, so it's an approximation. The kinetic energy is 1 over 2 m0 v square is the kinetic energy approximation. When the speed goes close to c, this no longer valid. Okay, so relativistic momentum. In relativity theory, momentum definition is expanded. The momentum used to be mv, now m is lambda m0, right? So go through some math manipulation. We get k minus k0 lambda minus 1 m0 c square. So the momentum become like energy. So the momentum, conservation of momentum, is actually conservation of energy. In classic physics, we didn't know where this conservation of momentum come from. Remember, we used to say one ball hit another ball, momentum P1 to P2 is going to be same after the collision. Okay, and the way we understand this exchange of the force is impact. The impact is the Newton's third law. The force is action reaction, works same way. So this gonna be mv and this amount is exchanged during the impact. So from P, this amount go to this side. This side gives some impact amount. So overall, it's conserved. Yeah, but using the relativistic word, the momentum become a kind of energy, and as energy preserved, the conserved, the momentum is also conserved. So conservation of momentum is understood at a higher level in the special relativity. Okay, and there are many other consequences of the relativity equations which you learn in the physics class. This is a highlight of all the result of special relativities. I hope you enjoyed this video, and please check step 3 and subscribe.